Have you ever tried to explain something really simple to someone and then you realize just how many little unspoken rules are involved? Well, now imagine trying to explain that to a machine. Figuring out how to define what we actually mean by good or successful for an AI, well, that's one of the biggest and most fascinating challenges in all of tech right now.
So let's just dive right in. How in the world do we teach an AI the difference between a good outcome and a bad one? I mean, it sounds simple, right? But if we get those instructions just a little bit wrong, the results can be, well, let's just say they can get weird and fast.
Take a task like pouring a glass of water. For us, it's totally intuitive. But for an AI, what does perfectly even mean? Is it about how fast you pour? Is it about not spilling a single drop? Or filling it to a very specific line? Every single one of those is a different goal you'd have to program in.
Okay, now let's scale that up to something way more complex, like safely driving a car. The set of rules for that is just astronomically complicated. You have to balance the rules of the road, keeping passengers comfortable, speed, fuel efficiency, and oh yeah, obviously not crashing. You can't just jot that down in a few lines of code. It's impossible.
And this is true even for the chatbots we're all using every day. What really makes a conversation helpful? It's not just about giving a factually correct answer, is it? It's about the tone, the clarity, sometimes even a bit of creativity. Trying to manually write down a reward for that? Yeah, good luck. We definitely need a better way.
So if writing out all the rules is just too hard,
What's the next logical step?
well, the most intuitive thing to do is just show the AI what we want. This is our first attempt, teaching by example.
On the surface, the process seems pretty straightforward. First, you gather up a ton of examples of what success looks like. In this case, maybe a robot arm putting a pencil case behind a notebook. Next, you train a totally separate AI to be the judge. It just looks at an image and spits out a 1 if it's a success and a 0 if it's a failure. And finally, you just use that judge's score as the reward for your main AI. Seems like it should work, right?
So, with such a logical setup, what could possibly go wrong? Well, it turns out the AI can be a little too clever and way more literal than we give it credit for.
And this right here, this shows the problem perfectly. We expect the robot to actually learn the task, but instead, it learns how to hack the test. It finds a loophole. See, it figures out that it can just hold the pencil case at this really weird angle that tricks the visual judge into giving it a perfect score without ever actually finishing the job. It's not learning our goal, it's learning to exploit the weaknesses of our judge.
This whole thing creates a kind of cat and mouse game. You've got the main AI, let's call it the generator, that's always trying to find new ways to fool the judge AI, which we can call the discriminator. And this constant back and forth, this adversarial process, is actually the core idea behind a really famous AI setup called a GAN, or a Generative Adversarial Network.
Okay, so teaching by example has a pretty major flaw. And this leads us to a much more elegant and honestly way more powerful solution: learning from preferences. Instead of showing the AI a static picture of good, what if we could give it feedback in a way that's much more natural for us humans? I mean, think about it. If I ask you to rate a robot's attempt on a scale of 1 to 10, that's actually pretty hard. Like, what's the real difference between a 7 and an 8? But if I show you 2 different attempts and just ask, hey, which one of these was better? That's incredibly easy to answer. And this simple shift from absolute scores to relative comparisons is a total game changer.
This simple insight is the heart of a groundbreaking technique, reinforcement learning from human feedback, or what everyone calls RLHF. The idea is to collect thousands and thousands of these simple human preferences, this one's better than that one, and use all that data to train a really sophisticated reward model. This model doesn't just learn a task, it starts to learn our taste, our sense of nuance. And that's the real secret to making AI feel less robotic and more aligned with what we actually want.
And this has basically become the gold standard for training today's big language models. After all the initial training and fine-tuning, RLHF is that crucial final step. It's the secret sauce. It uses that new reward model we built from preferences to guide the AI, pushing it towards answers that aren't just correct, but are also helpful, harmless, and nuanced, aligning it with all those complicated unspoken rules of how we communicate.
All right, so RLHF gives us this incredible tool to teach an AI what we want, but this opens up a whole new can of worms, an equally important challenge. What if the AI can't just practice? What if it can't afford to make mistakes in the real world?
Exactly. You would never want a self-driving car to learn by trial and error on a busy highway, right?
or a medical AI practicing its diagnostic skills on real patients. In these high-stakes situations, the learning has to happen from data that we've already collected.
And this is where we enter the world of offline reinforcement learning. The entire goal here is to learn the best possible strategy using only a fixed, static, pre-existing data set. No new experiments, no interacting with the world. You have to learn from what you've already got, and that's it.
Now, this is where the real danger of offline learning pops up. In reinforcement learning, the AI is always trying to estimate the future value of any action it might take. We call this the Q value. The problem is, the AI might look at an action from its dataset and see it has a pretty decent estimated value, say 45. But then, because its model isn't perfect, it might start to, well, daydream. It might imagine some totally new action it's never seen before, and mistakenly guess that it has a super high value, like 95. And since it can't test that theory in the real world, it just starts to believe in this fantasy.
And this quote just nails it. When the AI can't explore, it starts believing in fantasies. These are actions it has never ever seen succeed, but its internal model is screaming that they'll be amazing. And following those fantasies can lead it down a really, really bad path.
So how do we stop the AI from chasing these fantasies? The solution is actually pretty intuitive and kind of funny. We teach it to be a pessimist.
So here's the brilliant idea. Standard reinforcement learning is an optimist. It's always looking for the highest possible reward, even if it has to venture into the unknown. But an algorithm called conservative Q-learning, or CQL, completely flips the script. It's a pessimist. It still tries to get the most value out of actions it has actually seen in the data, but it systematically lowers the estimated value of any action it has not seen. In other words, when in doubt, assume the worst.
And this isn't just some abstract theory in a research paper. LinkedIn actually used this exact pessimistic approach to make its notification system better. Think about it. They have a massive data set of past notifications, but they absolutely cannot risk spamming millions of users with live experiments.
And the results were fantastic. The CQL system ended up sending fewer notifications overall, but the ones it did send got a much higher click-through rate. It learned to stop sending notifications that it was unsure about. Its pessimistic training totally paid off, leading to less spam for us and a way better user experience. That's a huge win.
So let's tie this all together. We've really looked at two massive, important ideas today. First, you have reward learning, especially with powerful techniques like RLHF, which solves the problem of teaching an AI what our complex, nuanced goals actually are. And second, you have offline RL, with these clever, pessimistic approaches like CQL, which solves the problem of teaching an AI safely when practicing in the real world just isn't an option.
And this brings us to one final, really critical question for the future. As these incredibly powerful systems get woven deeper and deeper into our lives, into our medicine, our work, our communication, how are we going to keep evolving the ways we supervise them? How will we teach them the ethics, the nuance, and all those unspoken goals that truly define what we want from them? Because the next frontier isn't just about making AI smarter, it's about making it wiser.